Imagine your favorite plant taking a long trip. It can't ask for water, it can't move toward the sun, yet it still needs care. What if its box could act for it? In robotics, everything starts with sensing, but ends with action. The actuation subsystem is where ideas become movement, light, or sound. It's how a robot changes its world. A relay works like a robot's fingertip. It lets a tiny digital signal press the power switch for bigger devices, safely and precisely. This pump acts as our little plant's heartbeat, circulating water whenever the soil gets too dry. And when the sun hides, our LEDs become a tiny star, giving light energy so the plant keeps growing, even inside the box. Here's our concept: a two-layer shipping box that keeps the plant alive wherever it goes. The top holds the plant, its light, and the water outlet. The bottom houses the brain, our Raspberry Pi Pico breakout board, and the actuators that make care possible. The relay acts as a switch, turning the water pump and LED sunlight on or off when conditions call for it. Together, these pieces form a tiny, self-contained life support system for a traveling plant. Now let's take a deeper look, starting with anatomy. Your bicep is the actuator. It's the muscle that creates force. But your hand? That's the effector, the part that actually touches the world. In our project, the pump's motor is the muscle. But the tube dripping water into the soil? That is our effector. We are using the muscle to power the hand. Next, how do we get things moving? If you need a battery or a plug to make it move, that is active actuation. Our pump is active. If we cut the power, the water stops. But if we just put a water tank on a high shelf and let gravity pull the water down through a valve, that's passive actuation. It uses nature's energy instead of a battery. Let's talk about a core robotics concept, degrees of freedom, or DOF. It's just a fancy term for how many different ways a robot can move. A complex robotic arm might have 6 degrees of freedom. It can move up, down, left, right, and twist in 3 different ways. A train on a track has only 1 degree of freedom, forward or backward. So how many degrees of freedom does our plant box have? 0. It's stationary, and that's the point. It's not a mobile robot, it's an environmental robot. Our focus isn't on moving the box. Our focus is on controlling the 1 degree of freedom of our actuator, the single rotational spin of the water pump motor that pushes the water where we want it. So why talk about this if our plant box sits still? Because in robotics, every degree of freedom costs you something: more code, more power, and more chance of failure. We intentionally designed our box with 0 degrees of freedom for locomotion. We want it to stay put. Instead, we spent our movement budget on the inside, the pump. It has 1 rotational degree of freedom. Good engineers know that limiting movement is just as important as creating it. But since this is a traveling plant, the world will move it. This is why, for design improvement, we can add an IMU sensor. It measures degrees of freedom like tilt and shake. If the IMU senses the box moving, detecting those forced degrees of freedom, it tells the brain, "We are moving. Stop the water." This is how understanding DOF helps us build a safety system. You now understand the theory, how the plant box works, active and passive actuation, degrees of freedom, and the difference. Next week, we are sitting down with the amazing Jessica Chavez to talk about her journey in robotics and the power of building your own technology. You won't want to miss it.